Welcome to the Crazy Hat Chemist. So here we go with another awesome video here with thermochemistry worksheet number two. Yeah, that's right, folks. All right, so before we get started on this first problem, just a little bit of prior knowledge to remind you of from the previous worksheet and some information here. Here we go. So thermodynamics equation, that's Q equals mCp times delta T. Q is the heat term, that is typically in joules. M is the mass. Specific heat capacity, that is in joules per gram degrees Celsius. And delta T is the change in temperature. The delta T is the final temperature minus the initial temperature. So if I substitute in final minus initial temperature into delta T, what do I get? Q equals mCp TF minus TI. We're going to be working with this equation quite a bit here. Okay. The other thing I'm going to remind you of is this generic heating curve. This is coming directly from my video lecture series, if you will, on this unit of thermochemistry. Okay. And you should know that along the y-axis is temperature, along the x-axis is heat, and then we have our idealized generic graph. This generic graph goes with these units right over here of our constants. And so we have a solid, liquid, and a gas as far as states of matter, solid, liquid, and a gas. Those are all sections which are sloped. And in between the solid and the liquid is the inner conversion between the solid and the liquid. In between the liquid and the gas is the inner conversion between the liquid and the gas. What does define this graph is the first flat line section, which is this inner conversion between the solid and the liquid, and that's the melting point. And then also the liquid and gas interconversion, and that is called the boiling point. So the first thing that you're going to do is draw this generic graph just like this, and then you're going to label the melting point and the boiling point as the first and second flat line sections respectively. That's probably what you need to do first. Okay, and then from there, we are going to say this is step 1, step 2, step 3, step 4, and step 5. You should see that the odd number steps 1, 3, and 5 have a change in temperature. And steps 2 and 4, the even number steps, do not have a change in temperature. And the constants along those steps relate to that as well as the equation. Okay, I do have the constants right above here for water specifically, so make sure that you use those for water. There are lots of different constants for water, so please, or whatever the compound or element is, so make sure that you actually pay attention to that. For whatever your textbook gives you, right? Let's see. A couple other equations and information that are really important is right here at the bottom, and that is the following. The thermal equilibrium equation is Q of A plus Q of B equals 0. This is when you mix two things together that have different temperatures or different heat contents. You can rewrite this so that you don't have that 0 term and move one of these over to the other side. That's Q of A is equal to negative Q of B. What this effectively says is that the heat is transferred from the hot object to the cool object. Heat always goes from hot to cold spontaneously in a net direction. If I were to replace what Q is equal to on each of these right here, then that's Q is equal to MC TF minus TI, and I have done that right here. And then see plus Q equals MC TF minus TI. I've done that right here, and that equals 0, equals 0. At thermal equilibrium, that means that there's no net heat loss or gain, and that's when the two temperature finals, the final temperature and the final temperature are the same, okay? The specific heat capacity for water is the really molar heat capacity. This is why this is called the molar heat capacity, because it's per mole. And that's joules per mole Kelvin. Another thing that I'm gonna remind you about, and that is that the change in temperature for Kelvin and the change in temperature for degrees Celsius is actually the same. So we don't have to worry about that, hopefully. All right, let's see what else we've got here as far as information that I want to relay to you at the beginning here. So the other information is I'm going to change that molar heat capacity for water, and we're going to change that molar heat capacity for water to an information that is familiar to you, which is 4.184 joules per gram Kelvin or 4.184 joules per gram degree Celsius. Again, the change in temperature for degree Celsius and Kelvin is actually the same. So we're pretty good with that. All right. And then the other information here is that you need to know that specific heat capacities are inversely proportional to the density. That is, the more dense the object is, the lower the specific heat capacity. The less dense the object is, the higher the specific heat capacity. You also need to know that specific heat capacity is really, if it's a small number for the specific heat capacity, that means it gains energy quickly and releases energy quickly. So also, if the specific heat capacity is very large, then it takes a long time to gain that energy, but it also takes a long time to release that energy. One other thing here is that the conversion between joules and calories is 1 calorie is equal to 4.184 joules. So that's a really nice one. We also need to know this equation for the enthalpy of a reaction. So that's the delta H, and typically this is a little zero right here as a naught. So delta H naught for the reaction is equal to the sum of the delta H naught of formation for the products minus the delta H naught sum of for the reactants. So it's NPR, that's naught products minus reactants. We also are going to be working with Hess's law of summation, and that's when we have two or more equations, we can add them up. All right, so let's get moving on to this first problem here on this worksheet here, which is going to be number 1. So let's set that up here for you, and let's see if we can hammer this worksheet number 2 out. All right, cool, y'all. Awesome. All right, so we're going to calculate the heat required in joules to warm 0.53 grams of water from 14.1 degrees Celsius to 55.4 degrees Celsius. So what I highly recommend doing is making a generic graph. Here's our generic graph, and what defines this graph is this melting freezing point and this boiling point. This is in degrees Celsius here. And I'm going to put on here my lowest temperature, and that's right here at 14.1, and my highest temperature, that's right here at 55.4. I'm just going to do this section right here in between here. So I'm only going to be doing if I one of the steps, and this is step number 3, right? 1, 2, step number 3, 4, and 5. Okay, so we're going to be doing step number 3. Effectively, step number 3 is Q is equal to MC delta T, right? So this is generic here, but we do have to look at the constants of which we are given within this problem. And I have given you constants for all of these right here at the top. So we're going to be using this information right here. You should see that this is joules per mole Kelvin. I'll change that to degrees Celsius in just a moment. Okay, and so let's start off with these numbers. All right, so the numbers that we're going to start off with, well, first thing I'm going to do is draw effectively a line in the sand, if you will, so that we can do this stoichiometry. It's really not too bad. Here we go. We're going to start off with our mass. That's 0.53 grams of H2O. H2O. Vertical stop here in between the next step, and you should see that this is grams, so I'm going to have grams down here, and that will enable me to cancel out my units as is appropriate. That's going to be grams of water. Another way to do this problem and starting off with it is actually to use the constant first, and it's going to be 75.40 joules per mole Kelvin or degrees Celsius. We can use either one of these. They are going to be the same because the change in temperature for degrees Celsius and Kelvin are the same. So you should see that I need to cancel out the moles in order to get joules as my final result. So I'm going to have moles up here like that, and that will enable me to cancel out the grams. So it's 1 mole of H2O is equal to 18.02 grams of H2O. H2O, and this is H2O right there. You should see that grams of water, moles of water are all canceling out right here. Okay, and now I have for units, thus remaining is joules per degree Celsius. So I'm going to have to do a change in temperature. It's going to be the final minus the initial temperature. The final temperature is 55.4 degrees Celsius, and the initial temperature is 14.1 degrees Celsius. Okay, so my degrees Celsius are going to cancel out right there, and I'm going to be left with joules, which is what I'm looking for. I'm going to have two significant figures on this problem here because I'm going to look at that 0.53. That's the least number of significant figures that I have in this problem. And I'm going to do 0.53 divided by 18.02 times 75.40, and then multiplied by the change in temperature for this right over here. And so that is going to be 92 joules. And there is my answer, two significant figures. Bam. All right. So that is problem one. Hopefully that made sense. Okay. Now, some people don't actually do this graph here. I would highly recommend that you do the graph because the graph really helps you and figures out, okay, where am I, where I need to be, and all that kind of stuff. All right. Okay. So sliding this away. Let's try out this next problem here. Problem number 2, let's get that set up here, looking good. All right, problem number 2, it says, calculate the specific heat of an unknown metal, knowing the following data obtained in the lab. It says we have 0.0053 kilojoules of heat is required to raise the temperature of 0.23 gram of a metal from 22.07 to 75.8 degrees Celsius. All right, so really what we're doing is Q is equal to mCp delta T. So we're going to be using that equation right there. Okay, this is my Q term. This is my M term. And this difference here is going to be my delta T. And I am solving for the change in temperature, which, excuse me, I am solving for the specific heat capacity, which is right here. So highlighted what we're solving for right there. All right, so a couple of things that we want to do is the specific heat capacity is going to have units of joules per gram degree Celsius. So I'm going to make sure that I get those units. So the first thing I'm going to do is I'm going to convert my Q from kilojoules into joules. So that's a really simple one, 0.0053 kilojoules is going to equal 1 kilojoule is equal to 1,000 joules. And that will enable me to convert this into joules. And so that will be 5.3 joules. So that's the amount of heat, right? We're moving this decimal 1, 2, 3 places effectively when we multiply. So this is going to be my Q term. Another thing that we're going to do here off to the side is we're going to get our delta T. And our delta T is going to be the final minus the initial temperature. So delta T is going to equal the final temperature of 75.8 minus the 22.07. So delta T is going to equal, we're going to subtract these two numbers here, and we're going to round to the fewest number of decimal places. This has 1 and this has 2. So my change in temperature here is going to have 1 decimal place. So that's going to be 53.7 degrees Celsius, rounded to 1 decimal place. So now I have my delta T, I have my Q term, and let's see, what else are we missing? Well, we already are given the mass, and that has the correct units, so that's perfect. What I'm going to do is rewrite this equation. Q is equal to mCp delta T, and what we're going to do is we're going to rearrange this and solve for the specific heat capacity. So I'm solving for Cp. So I'm going to divide both sides by m delta T, divide by m delta T. These cancel out, and I'm left with Cp is equal to Q over M delta T. And what I've done up here is I have just circled in red all the little parts that we need. So we have the Q term. This is the 5.3 joules. We have our M term. That's right here. That's our mass, 0.23 grams. And then we have our change in temperature term, and that is the 53.7 degrees Celsius. So I have all my parts here. I have two significant figures, two significant figures, two significant figures, leading zeros don't count, and three significant figures. So my ending answer is going to have two significant figures. I'm going to take 5.3 divided by 0.23 divided by 53.7, and I'm going to round that to two significant figures, and I'm going to have 0.43 joules per gram degrees Celsius. And I'm going to ask myself, does this number actually make sense for a specific heat capacity? For a specific heat capacity for a metal, it should be less than 1. So that number most certainly makes sense. Okay. All right. So that's problem number 2. So let's peel that away, and we're going to work on problem number 3. All right. Sweet. Here we go. All right, says calculate the final temperature of Naria, the one of the 3 rings forged by the elves of Elgaron and given to Gandalf. Naria is composed of 198.9 grams of metal. The specific heat capacity is 0.101 joules per gram degree Celsius and is heated to 1,695 degrees Celsius and is dropped into Tom Bobadil's cup filled with 509 milliliters of tea, mostly elven water, with a density of 0.930 grams per mil, which was originally at 292.5 degrees Celsius. All right, bringing in a little bit of the Lord of the Rings into your life here. So we're going to figure out what equation we're using first. So we are using QA plus QB is equal to 0. And this is when we are plugging into the thermal equilibrium equation. On the first worksheet, I actually used this one. So what we're going to do is we're actually going to subtract Q of B on both sides. And what we're going to get is the following equation. Q of A is equal to negative Q of B. Okay, and we're going to work with this one. I'm going to do this one here because on the previous worksheet number 1, I just plugged directly into here. So I'm going to show you the 2 different ways of doing it. And then the next thing that we're going to do is we're going to call A the ring. We're going to call A, this is going to be the ring. Gandalf's ring, and then this is going to be Tom Bobadil's cup filled of water. This is going to be the water. Okay. All right, fantastic. It doesn't matter which one you call A or B. And then we're going to substitute in what A is equal to and what B is equal to. And so I'm going to rewrite those equations here. So I'm going to substitute what Q of A is. Q of A is going to be M CP TF minus TI. This is going to be for the ring. Okay. Is equal to, and I'm going to make sure that we don't forget about this, negative, and then I'm going to put brackets around this so that I define this absolutely here for you so that you can clearly see it. And this is going to be MCP TF minus TI, and then this is going to be for the water. Okay, hopefully you can clearly, distinctly see that. What we are solving for is what? Calculate the final temperature of the ring. And so the final temperature of the ring, I'm going to highlight that. So the wonderful thing about this thermal equilibrium equation is that the final temperature of both substances, that is the ring and the water, are going to be the same. So both of these are going to be the same value. So what I'm going to do is I'm going to plug in the information that is given in this problem right into this here. And so we're going to have 198.9 grams. That's the ring. We are given a specific heat capacity for Gallon-Dallas ring, joules per gram degrees Celsius. And we are solving for the final temperature, that's TF, minus 1,695 degrees Celsius is equal to, I'm going to place this here, negative, and then that brackets here, so that works for us. And then we have 509 milliliters. But we need to get the mass of this, and that is we're going to use the density, grams per mil. Okay, this term right here will give us the mass because you can see that the milliliters cancels out. And since it's Elvin cup of water, it's mostly water. We're going to use this specific heat capacity for water, and that's 4.184 joules per gram degree Celsius. And then let's just make sure that we have barely enough space here. TF minus, and this term right here is going to be 292.5 degrees Celsius. I've kind of run out of space here for that. I apologize, but that's going to be giant brackets there like that. All right. All right. Fantastic. So now what we need to do is we just need to solve this here. And again, what we are solving for is TF. And we're going to call this X, okay, for simplicity's sake. And then the other thing that we're going to do is we're going to get rid of all the units so that we work on just solving this. And since we're solving for X, we're not going to round until the very end of this problem. Okay, so I'm going to get rid of all the units and I'm going to replace TF with X. So I'm going to slide this on up. And there's what we got so far. Sorry about the bell there. Keeps on happening. No worries. All right. And so then what we're going to do is we are just going to multiply these two values right here, and we're going to multiply these three values right here. And this product right here, 198.9 times 0.101, that is going to equal this number here, 20.0889. And then my final temperature, that's going to be my X term right here, minus the 1695 is equal to negative. And what we're going to do is distribute. So we're going to multiply this and we're going to distribute out that negative sign. 1,980.58008X. And we're distributing this and pull. Oh, wait. I apologize. So I'm going to rewrite this here because I've made just a little bit of an error. So I'm going to cover that up. Let me try that again. I apologize. Here we go. Let's try this again here, folks. So I'm going to take the product of these two, and that is going to be equal to 20.0889. There we go. X minus 1695 is equal to negative, forgot about my negative in my brackets, 1980.58008 X minus 292.5, and then there's my brackets again. Okay, cool. All right, so that's looking good. We're going to slide this up a little bit more here, and hopefully you have all this here. And now what we're going to do is we're going to distribute this number over both these terms. We're going to distribute this number over both these terms, and we're going to distribute that negative sign over both those terms as well. And then we're going to end up with the following here. Okay, so what we have is 20.0889x minus 34,050.6855 is equal to negative 1980.58008x plus 579,319.674. Okay. All right. And then what we're going to do is we are going to combine our like terms and then our other like terms right there. Okay, and so we're going to take all our like terms and our non-like terms. We're going to take all the x terms to one side and all the non-x terms to the other side. So let's do that right now. All right, so here we go. Sorry, it's a little bit sloppy here, but we are going to combine our x terms. Make sure that you include that negative sign in that. There are our x terms right here. And then we're going to combine our non-x terms that are right here. And we're going to move all the x terms together on all the non-x terms together. So we're going to get the following numbers here. Okay, so we've got 2000.66898x is equal to 613,370.3589. And then to solve for x, we're going to divide both sides by this number. This is really a solve for x problem. Slide this up a little bit. X is going to equal 306.5. And then we're going to round this to three significant figures of which were originally in the problem. So X is going to equal 307. And we're going to put units on this, back on this, and this is degrees Celsius. That is our answer. All right, so I think what I'm going to have to do is zoom on out here just a little bit so that you can see this entire problem here right there like that. Okay, so we've got the thermodynamics equation. I've moved over one of the terms and then I've substituted in what each of the parts are for it. I've plugged in the mass for the ring, the specific heat capacity for the ring. I'm solving for the temperature, the final temperature of the ring. I have the initial temperature. Then I have the volume of the water and the density of the water. That's the T. The product of these two is going to equal my mass. The specific heat capacity for the water, the final temperature is what I'm solving for, which is the same for the water and the ring, and then the initial temperature. Then mathematically, what we're going to do is multiply these two numbers, and I'm going to get this number right here of 20.0889. I'm going to take the product of these three numbers, and I'm going to get this 1980 number. Then I am going to take the TF and I'm going to substitute in for X. And then I'm going to take my TF, substitute it in for X. And then I have my other numbers of my initial temperatures of both the ring and the water. And then it's just a matter of solving for X here. And so we're going to distribute this 20 over both the terms inside the parentheses. We're going to distribute the negative sign and the 1980 over both the terms inside the parentheses. We're going to get X terms. We're going to get non-X terms. We're going to combine our X terms and our non-X terms and move them separately and then divide by the coefficient in front of the X. And then we're going to get our number. We're going to round it to the three significant figures of which the number is that I have originally in the problem. Cool. Hopefully that worked out well for you. Follow along. And now what we're going to do is we're going to do the next problem. That's problem number 4. Bam. All right, so I'm going to peel this away and we're going to do problem number 4. Okay, zoom in on here so we can hammer out problem number 4. All right, let's see, here we go. By the way, a little bit of advertisement here. This video here is sponsored by the Crazy Hat Chemist. I am the crazy hat chemist, and that's why you're watching this video. Hopefully that you can learn some good chemistry here. All right. Whether it's early in the morning, in the afternoon, or late at night, I'm always here for you. You can watch this video at any time, in other words. Okay. All right. So here we go. Problem number 4. Determine the heat in joules that's required to heat 0.37 grams of water from -8 degrees Celsius to 119 degrees Celsius. So this is one of those. I'm going to draw a graph problem. So drawing a generic graph here. Okay. And this is water. So consequently, this is a 0. Consequently, this is 100. My lowest temperature is -8. That goes right here. My highest temperature is above the 100. So I'm going to go step 1, step 2, step 3, step 4, step 5. I'm going to do all 5 steps on this problem here. That's the whole plan. And then I'm going to sum up all those values. And then that's going to equal what I want. I'm going to be using the constants that were at the top of this worksheet originally. And let's see if we can slap that back on here again. So we did problem number 1, and we have some constants here. This is for the specific heat capacity for ice. This is the specific heat capacity for water. This is the specific heat capacity for steam. This is the heat of fusion, and this is the heat of vaporization. We're going to be using these 5 constants. This is going to be for step number 1. This is going to be for step number 3. This is going to be for step number 5. This is going to be for step number 2, and this is going to be for step number 4. Okey-doke. You should see that the 1, 3, and 5 have Kelvin in the denominator. I'm going to change that to degrees Celsius. So because the change in temperature, or the change in Kelvin, and the change in degrees Celsius is actually the same. And then the heat of fusion and the heat of vaporization, this is the first flat line section, the second flat line section, and there is no temperature term in here, and that should make sense. So I'm going to peel this away, but this is where these constants are coming from, is directly from this worksheet at the top. So I'm going to peel this away. I'll be using these constants here. Boom, peeling that away. All right. So here we go. Step number 1 is going to be right here. So number 1. And so let's see here. We'll just draw a little line here so we can, let's see if that will be long enough or not. All right, so we have a 0.37 grams of water, and we're going to be using the, for step number 1, the molar heat of ice. And so that value has moles in it. So we're going to have 1 mole of water, and that's 18.02 grams of water. And the constant is 37.8. That's joules per gram, degrees Celsius. And the final temperature is 0 minus the initial temperature, and in this case, it's -8.0. That's degrees Celsius. It's going to equal some value here. You should see that the reason I'm doing this is the grams cancel, the moles. Whoops, I apologize. This is actually moles. The moles cancel, and the degrees Celsius cancels, and what does not cancel are the joules. So that's perfect. All right. So now what we're going to do is step number 2. Where is step number 2? This is step number 2 right here, this rectangular box. Okay, that is going to be the heat of vaporization, of which I'm going to be using at that section. Okay, we are starting off with the same mass. The mass never changes in these problems, which is a beautiful thing. And then I have 1 mole of H2O, and that's 18.02 grams of H2O. All right. And then I'm going to be using the heat of fusion, which is 6.01 kilojoules per mole. There is no temperature in this section here because it's the flat line section. And I'm going to convert these kilojoules, 1 kilojoule into joules. And that's right there like that. That's step number 2. Step number 3. Let's draw a line right here. for step number 3. Okay, perfect. So our 0.37 grams, we still have that. By the way, where are we? We are doing this step right here on our graph. It's 1 mole of H2O and 18.02 grams of H2O. And then we are going to use the molar heat of water, and that is 75.40 joules per mole degrees Celsius. That's moles right there. And then our final temperature in this section is 100. So that's 100 minus the initial temperature, that's 0, and that's degrees Celsius. These have an infinite number of significant figures. It's not, it's just defined in that section of the graph. All right, now step number 4. Step number 4 is the second flat line section. We're using the molar heat of vaporization. So let's draw this out. And we have our 0.37 grams. We have our 1 mole of H2O, and we have our 18.02 grams of H2O. And heat of vaporization, and that is 40.7 kilojoules per mole. Again, there is no temperature in this section because it's a flat line section, but we're going to convert the kilojoules into joules, and then we're going to get a value for that. All right. And then we have one more step. That's step number 5, the final step. And let's see if we can knock that one out of the park here. And let's see, I'm going to just zoom on out just a little bit so that we can get this whole thing on one. That's our goal here. All right. So where are we on the graph? We are on this section on the graph right there. So we're going to have 0.37 grams. 1 mole of H2O and 18.02 grams H2O. And then we're going to use the molar heat capacity for steam, and that's 36.5 joules per mole degrees Celsius. Our final temperature is that final temperature of the problem, and that's 119. And then our initial temperature within this section is 100. So minus 100, and that's degrees Celsius. On every single one of these steps, you should see that we get units of joules. So everything cancels out. Grams, moles, degrees Celsius, joules. Grams, moles, kilojoules, joules, grams, moles, degrees Celsius, joules, grams, moles, kilojoules, joules, and joules. So every single one of these steps has joules. Okay, we're going to have 2 significant figures for every single one of these steps. So you're going to do the calculator math associated with these. So plug these into your calculator. You're going to have 6.2 joules. Then you're going to have 120 joules. That trailing 0 does not count because I have 2 significant figures. 150 joules. That trailing 0 does not count because I have 2 significant figures. 840 joules. That trailing 0 does not count because I have 2 significant figures. And 14 joules. And then what we're going to do is we're going to add up these 5 numbers here. And then when we add up those 5 numbers, we're going to be rounding to the tens place. Okay, so this is in the 10th position. This is the most precise measurement of all of them. And this step, and this step all have the same least amount of precision, which is they are precise in the tens column. So my answer, after I sum all 5 of these numbers up, is going to have an answer rounded in the tens column. And so this is my final answer, 1,130 joules, and that's rounded to the tens place. That's right there with that 3. All right. So that is problem number, what was it? Problem number 4? Yeah, that was problem number 4. All right, fantastic. We just nailed out 4 problems. Now we're going to move on to problem number 5. Let's see if we can knock that one out of the park. Okay, Number 5. Here we go. Number 5. Okay, number 5 is going to be very similar to problem number 4, except that it's a different section of the graph. It says calculate the heat in joules required to heat 50.9 grams of water from 5.3 degrees Celsius to 103.7. So again, what we're going to do is we're going to do this generic graph here. And since it's a water problem, that means that this is 0 and this is 100. That defines the graph. What is our lowest temperature? That is 5.3. So we are somewhere right here. We're above the freezing point. What's our final temperature? That's right over here. So we're going to be doing, this is step 1, this is step 2. So we're going to be doing step 3. We're going to be doing step 4 and then step 5 and then adding them all up. So step number 3, step number 4, step number 5. And again, what I am referring back to are the constants that I had at the very beginning of this worksheet. We're going to be doing step number 3, step number 4, and step number 5. We're not going to be doing 1 and 2. So we're going to be using these 3 constants, 3, 4, and 5 for this problem. So let's see if we can do that. So this is going to be step number 3. And let's see what we got here. So we have 50.9 grams. And for step number 3, that is the molar heat capacity for water. That is in joules per mole degrees Celsius. So we are going to go from 1 mole of water and the 18.02 grams of water. And then we're going to use that 75.40 joules per mole degrees Celsius. And our final temperature here is 100. That's 100 minus our initial temperature right here, which is 5.3. 5.3, that's degrees Celsius. We're going to get some number for that. We'll come back to that in just a bit. Then there's step number 4. Step number 4 is the heat of vaporization. That's the constant that we're using right there is the heat of molar heat of vaporization. Okay. And so again, we have the same 50.9 grams and 1 mole of H2O and 18.02 grams of H2O. And then we have that constant that we have, which is 40.7 kilojoules per mole. And again, there's no temperature units in here in the denominator because it's a flat line section. Hopefully that makes sense. We're going to convert our kilojoules into joules. And that's done with this simple conversion right there. Then we have one more step. This is going to be step number 5. And here we go. Step number 5. It's going to be the same 50.9 grams. And we are using step number 5. That's right up here. 1 mole of H2O and our 18.02 grams. That's the molar mass of water. And then we are going to be using the constant for steam, the molar heat of steam. And that's 36.5 joules per mole degrees Celsius. And the final temperature here is our 103.7. Our initial temperature is right there at the 100. And that 100 has an infinite number of significant figures because it's defined, right? So let's zoom on in there just slightly like I had before. Okay, perfect. Now what we're going to do is we're canceling out our units of grams, moles, degrees Celsius, and we're left with joules, grams, grams, moles, moles, kilojoules, kilojoules, joules, grams, grams, moles, moles, degrees Celsius, joules. So all of these will have joules. I'm going to have 3 significant figures for each one of these. So I'm going to have 20,200 joules and then 115,000 joules and 381 joules. Then what we're going to do is sum all these up. I'm going to use the least precise measurement, which is this one right here, and its precision is in the thousands column. So when I add these up, I'm going to have a number rounded to the thousands column. So I'm going to have 136,000 joules. And that is my answer right there. Whew, oh my gosh. Problem number 5, knocked it out of the park, folks. Absolutely. So now we're going to move on to problem number 6. All right, problem number 6, and it says here, what does it say here? Problem number 6. It says we're going to calculate the heat of a reaction in kilojoules for Pb plus PbO2 plus 2H2O yields 2 PbSO4 plus 2H2O, given the following information. Got 2 equations, and I got some enthalpy changes under standard conditions for both of those. All right, so, well, let's see here. We're going to draw a line in the sand, and we're going to put an arrow down. And then I'm going to rewrite what this equation is that I want. It says it yields 2 PbSO4 plus 2H2O. And then here I got 2H2SO4 plus PbO2 plus Pb. Okay. All right. So this is what I want. I'm going to have to solve for the enthalpy change for this reaction. That's really my question mark. That's what I want to get. All right. So how do I get to there? So couple of different ways. I'm going to call this A and I'm call this B. And what we're going to do is we're going to draw 3 arrows. 1, 2, and 3. And here we go. Just like this. And what we're going to do is we're going to rewrite the equation, the net equation that we want, which is right here, which is given in the problem right here at the top. We're going to write that down here. So we've got 2H2SO4. We have plus PbO2 plus Pb. And it yields 2 PbSO4 and 2H2O. What are we trying to solve for? The enthalpy change for this reaction. So don't know that. That's what we're solving for. All right, so I need to figure out how I get this by given equations A and B. Okay, so let's see here. So what we have is PbSO4. Let's see if we can find that. It's PbSO4 right over here. I see that right there on equation A. Do I see an equation B? No, I don't. This is the only PbSO4. Where does it need to be? It needs to be on the product side. Is it on the product side? No. So what I'm going to have to do is I'm going to have to flip this equation. When I flip the equation, I'm going to multiply by -1. Furthermore, it has a coefficient of a 2. Does it have a coefficient of a 2? No. So therefore, I'm going to have to multiply this equation by 2 as well. So what I'm going to do is I'm going to rewrite this equation, flipping the equation, and then multiplying by 2. So the first thing I'm going to do is I'm going to flip the equation. So I'm going to take this PbSO4, I'm going to put it PbSO4 on the product side, and then I'm going to write the Pb here, and the plus the PbO2 plus the SO3, okay? And then what I'm going to do is multiply by 2. So when I multiply by 2, this will have a 2, that will have a 2. This will have a 1, that's going to have a 1. This will have a 1, that will have a 1. And then this will have a 2, have a 2, just like that. Cool. So what do I do to the number here? So I have this 387.2. I'm going to multiply that by -1 by flipping the equation, and I'm going to multiply it by 2 by multiplying the equation by 2. All right. Then the next thing that I notice here is I've got this H2SO4, and there's the H2SO4. It needs to be on the reactant side. It is sadly on the product side. So what I'm going to have to do is I'm going to have to flip this equation too. So when I flip the equation, I multiply by -1. Okay. So I'm going to have this H2SO4 not on the product side, but it's going to be on the reactant side. So I'm going to write that down as H2SO4 and then SO3 and H2O, just like that. All right, so I've flipped the equation, so that's effectively multiplying by the -1. I also need this coefficient of a 2. So I'm going to multiply the equation by 2, and I'm going to multiply that number by 2. So 2, 2, and 2. So what that gives me is this -113.5. I've flipped the equation, that's times -1. I've multiplied the equation by 2, and that's that 2. Now, what we want to do is make sure that things cancel out and add up to what we want. So this 2SO3 is on the product side. This 2SO3 is on the reactant side. They both cancel out. Perfect. All right, I have a PbO2. That's the PbO2. I have a Pb. I have a Pb. I have a 2H2SO4. 2H2SO4 yields. All my ducks are in a row. Again, follow my video. And then 2 PbSO4, 2 PbSO4, and 2 H2O, 2 H2O. Okay, fantastic. So I have crossed out what is necessary, added up what is necessary as well. Now what we're going to do is 387.2 times -1 times 2. And that value is going to be -774.4. And these values are in kilojoules, so this is kilojoules. And then I'm going to take 113.5 negative times -1 times 2, and that's going to equal 227 kilojoules. And then I'm going to take this number and this number. I am going to add them up, and that is going to be negative 547.4 kilojoules. But I need to round this to the fewest number of decimal places here. I think this was a 0. There we go. So that has one decimal place. So I have -547.4 kilojoules. And because this is negative, that means that this is exothermic. That means it liberates heat, it gives off heat. All right. Whew, that is a Hess's law problem. That is the sum of two individual reactions gives us the net equation. All right, so let's see if we can move on to the next problem. Perfect, that's number 6. Moving on to number 7. Number 7, magic number 7. Here we go. Here is number 7. And this is the second to last problem here, number 7. All right. So number 7, it says determine the heat of reaction in kilojoules for 3 3H2 plus N2 yields 2 NH3 gas. You will need to use the following standard heat of formation as well as some additional assumed known values. And so we have this ammonia. This is NH3. That's for ammonia. Let me see if I can make sure that that's focused. I'm not sure if it was. Okay, there we go. All right, so this is an enthalpy of reaction, and so we're going to use this equation. Delta H naught for the reaction is equal to the sum of the products, delta H naught of formation of products, minus the sum delta H naught of formation of reactants. This is what we're using. It's this fancy dancy equation. This summation, sigma, means sum of. So we're going to sum up the products, and then we're going to minus and the sum up of the reactants. Okay. So here we go. We're going to plug in some numbers. So delta H naught for the reaction is equal to the products. What are the products? Well, this is the product right there. There is actually a single product in this problem. Okay, and it's 2 moles of this. So 2 moles of that thing, which is ammonia, that's NH3. And the value for that is negative 46.19 kilojoules per mole. Okay, and notice that the moles are canceling out here, and I'm going to be left with kilojoules. Minus brackets. Oh, by the way, did you know that this video is sponsored by who? The Crazy Hat Chemist. That's right, folks. Subscribe to my YouTube channel and give me a thumbs up. Where's the thumb? There's a thumb. Give me a thumbs up. Boop, thumb. All right. Anyways, that was kind of weird. Just too early in the morning. All right. Some of the reactants. The reactants are hydrogen and nitrogen. And so you were not given some values for the enthalpy changes for the hydrogen and the nitrogen. And here's why. It's because both hydrogen and nitrogen are elements in their standard state. That is, hydrogen is a diatomic and it's a gas. Nitrogen is a diatomic and it's a gas. So that means that those values are 0. So that makes this problem like super, super simple. Okay, so let's see here. Here we go. We're going to say 3 moles of hydrogen is equal to 0 kilojoules per mole. Again, it is an element in its standard state plus 1 mole of nitrogen. And since it's an element in the standard state, that means that this is 0 kilojoules per mole. No way. Did you see that? That means that this term goes to 0, this term goes to 0, and that makes that this is a really simple problem here. So the delta H naught for the reaction, so the change in enthalpy under standard conditions for the reaction, standard conditions is 25 degrees Celsius and 1 atm pressure, atmosphere pressure. That's what that little 0 superscript naught means. That's how it's read. So it's 2 times negative 46.19, and I'm going to get negative 92.38 kilojoules. And that is my answer to 2 decimal places, because that has 2, and that's an infinite number of significant figures. And then this number is negative. That makes this exothermic. If that number were positive, then it would be endothermic. Okay. Okay, folks, we have one more problem to do on this worksheet, and then we are rocking solid for this entire worksheet of thermochemistry number 2. All right, here we go. Let's see if we can hammer out this one. All right, so suppose you have 2.3 mils and density 0.789 grams per mil of ethanol, C2H6O, at negative 5.4 degrees Celsius, and you increase the temperature until all of the ethanol has reached a temperature of 83.7. How much heat in joules does it take to heat the ethanol? The specific heat is, the heat of vaporization is, the melting point is, and the boiling point is. All right, so this is like if I go back to problem number 1, it's like problem number 1. It is like problem number, where did we go? Problem number 4. It's like problem number 4. It's like problem number 5. It's like problem number 5. But it's for ethanol. So what we have to do is draw ourselves a little graph. So we're going to draw a graph. And again, what defines the graph is the melting point and the boiling point. And what is the melting point? The melting point is negative 114. What is the boiling point? It is 78. So it says we have ethanol at negative 5.4. Negative 5.4. That means it's right here. It's above the melting point. That means this is a solid, this is a liquid, this is a liquid. And you're going to increase the temperature until all the ethanol has reached 83.7. And that is 83.7. That's right here. So that makes sense, hopefully. Okay. So we are going to do this problem here as the following. We're going to go 1, 2, and 3. All right, so we'll do that here in just a second. All right, folks, so here we go. We're going to do this step right here, step number 3. Okay, And so we're going to slide this along right here, just like this. Okay. So step number 3, we're going to have 2.3 milliliters. And the density, 0.789 grams per mil. That will cancel out our milliliters. And this step here, we're going to be using the specific heat capacity that is 112.4 joules per gram degrees Celsius. And then it's 78. 78 is our final temperature. And then our initial temperature is so minus negative 5.4. That's degrees Celsius. This is going to be a value. Then we're going to do step number 4. You should see that the grams cancel, the degrees Celsius cancels, and I'm left with joules right there. Now we're going to do step number 4. Slide this over. We've got our 2.3 milliliters, our 0.789 grams per mil. And then we're going to use the heat of vaporization, and that is going to be 38.56 kilojoules per mole. And so our milliliters cancel out, but our moles and grams do not yet. So what we need to do is deal with that. So we're going to use the molar mass. That's 1 mole of ethanol is 46.07 grams. That will cancel out the grams, the moles, and now I need to cancel out those kilojoules. 1 kilojoule, 1,000 joules, and therefore the kilojoules cancels out. I'm going to get a number for that. Then it's the final last step, and that is step number 5. So let's see if we can knock that one out as well. It's still the same 2.3 milliliters with a density of 0.789 grams per mil. And the specific heat capacity is going to be the same for steps 1, 3, and 5 here for the ethanol, because no other number was given. So this is 112.4 joules per gram degrees Celsius. And the final temperature is 83.7. And the initial temperature is that boiling point of 78 degrees Celsius. And then you should see mils, grams, degrees Celsius cancel. I'm left with joules. So we're going to get the values for those. All right. So we're going to shove all these numbers in our calculator here. And this one here is going to equal 17,000 joules. That's 2 significant figures. And then 1,500 joules. And then 1,200 joules. And what we're going to do is we're going to add all of these up. And that number, let me slide this up just a little bit. That number is going to be 19,700. But what we do need to do is have this to the thousands column. So I'm rounding with that 7 right there. So that's what we get when we add all these up. But we're going to add 1 to the preceding digit. That will cause us to have to put this into exponential notation. So our final answer for this here, I'm going to write this right up here, is 2.0 times 10 to the, and I believe that's 4 joules. And that is our final answer when we add up all those numbers together. All right, fantastic. I am the Crazy Hat Chemist. That is a badass video, and I hope you loved it. So please subscribe, and I'll see you next time. Bye for now. Bye.